And today I'm going to continue the discussion of last time. Now here is our overall project, and here's where we are in the construction of the course. For the first half of the course, I'm going to teach you what I think is the less interesting part of the subject, but I differ from most philosophers. They think it's the heart of the subject, and that is what I call mainstream philosophy of mind. And mainstream philosophy of mind is largely about the mind-body problem. There are other parts to it, like other minds and free will, but the mind-body problem is the big deal. How does the mind fit in? And the dominant view is some kind of materialism. Now, I think that's changing. I think materialism is less of an orthodoxy now than it was 20 years ago, but it takes a long time. And the dominant view thinks that unless you accept some kind of materialism, you're in bed with Descartes. You're forced to some sort of Cartesian dualism, and that's just the worst thing that could ever happen to a human being, is to be a Cartesian. So we had a series of materialist efforts. And now, last time we were considering arguments against materialism, and I went through a whole bunch of those just to remind you, and not necessarily in the order I gave them last time. We had absent qualia, which says, well, the problem with those theories is they leave out the qualitative character of experiences. They leave out the qualia. Another related argument is spectrum inversion. You can imagine an inverted spectrum for a section of the population, but it would be a different fact, but it would never show up in behavior. It would never show up in the third-person phenomena because it's entirely interior, it's entirely mental. All of these arguments, I think, have the same structure. And then there's Nagel, what it's like to be a bat, and Frank Jackson's what Mary knew. I'm just abbreviating all this so you remember what it was. And then I think, in a way, the most powerful of these is the zombie argument. The zombie argument says, well, you can imagine a being that was exactly like me in all of its behavioral respects, and maybe even in all of its structural respects, but all the same was a total zombie, had no mental life, whatever. This kind of mirror image of a famous argument in Descartes. Descartes says, I must be identical with my mind because I can imagine my body not existing, but I can't imagine myself not existing. This one says, I can't be identical with my body because my body might have there might be a body exactly like mine that had all of my behavior without any mental states, but that's not me. I have mental states in addition to the bodily states. So it's a kind of mirror image of an old argument. Okay, now we got these arguments, and now I want to take up some others. The next one is Kripke's argument about rigid designators, and this is a famous argument. And then we're going to get to one that I think is kind of fun, though. I've said it before. It's called a Chinese room. You'll hear about that one in a few minutes. But let's take care of Kripke first. Kripke says if you look at expressions that refer to objects, expressions like the President of the United States or Barack Obama, those refer to objects, but he says there are two different kinds of expressions that refer to objects. There are those that are what he calls rigid and those that are non-rigid. And a rigid designator is defined as an expression that refers to the same thing in all possible situations, in all counterfactual situations. And philosophers have an unfortunate piece of jargon. They say it refers to the same thing in all possible worlds. Now let me give you an example of the distinction between the rigid and the non-rigid. As a matter of fact, Benjamin Franklin is the guy who invented daylight saving time. Okay, now so we can refer to Benjamin Franklin either as Benjamin Franklin or the inventor of daylight saving time. But those are different because the expression Benjamin Franklin refers to the same guy in all possible situations, even in a situation in which he didn't invent daylight saving time. But the expression, the inventor of daylight saving time, does not always refer to the same guy in all possible situations, because we can imagine a different kind of situation, one in which Thomas Jefferson invented daylight saving time. So the inventor of daylight saving time is non-rigid. But Benjamin Franklin is a rigid designator, always refers to the same person in any possible world or in any possible counterfactual situation. Now, of course, if I name my dog Benjamin Franklin, I always name my dogs after philosophers anyway. That doesn't count because we're talking about the same usage. Given the same usage, the same meaning, so to speak, then the expression Benjamin Franklin is a rigid designator. The expression the inventor of daylight saving time is not a rigid designator. Benjamin Franklin invented so many common sense things, it's hard to imagine how could we have lived without these things, and why did we have to wait for him to think of them? Daylight saving time, the rocking chair, bifocals, what else? He invented all kinds. The Franklin stove, so he didn't send all the heat up the chimney. Various other things, just kind of common sense inventions that we all take for granted now, were invented by Ben. Okay, anyway, now says Kripke, if you take general terms, some of them are rigid and some are non-rigid. If you take the expression water, that's a rigid designator. If you take the expression H2O, that's also rigid. But if you take the expression grandma's favorite drink, or the stuff I used to wash my face with, those are non-rigid designator. Grandma prefers water, but she might have preferred tea. I wash my face with water, but I could have used gin if I was short of water and had a surplus of gin. I mean, it's hard to imagine. But anyway, use your own imagination. Okay, now here's the point, says Kripke. Wherever you have an identity statement of the form A equals B, if the expressions on both sides are rigid, then since a rigid designator refers to the same thing in all possible worlds, then the statement will be necessarily true because it's true in all possible worlds. That's a kind of heavy mouthful, so let me say it again. The idea is this: if you have an identity statement of the form A equals B, then if both expressions are rigid, the statement must be necessarily true. Why? Because since rigid designators refer to the same thing in all possible worlds, and since a necessary statement is a statement that's true in all possible worlds, then if the statement is true at all, it must be necessarily true. Okay, did everybody get that? I'll illustrate it with examples so it'll become clearer. So, says Kripke, the statement, water is grandma's favorite drink, that is not necessarily true. Grandma might have preferred beer or iced tea or any other possible drinks. And we can imagine a possible world in which that's not true. But if you say water is identical with H2O, that's necessarily true, because both water and H2O are rigid. They refer to the same thing in all possible worlds. Similarly with proper names. If I say Mark Twain is the author of Huckleberry Finn, well, that's an identity statement. Mark Twain is identical with the author of Huckleberry Finn, but the expression, the author of Huckleberry Finn, is not rigid, so that's not necessarily true. You can imagine a world in which he wasn't identical with the author of Huckleberry Finn, in which nobody wrote Huckleberry Finn, in which he died in a drunken stupor before he ever wrote the book. Okay, but if you say Mark Twain is identical with Samuel Clemens, that's necessarily true, because any world in which Mark Twain exists and which Samuel Clemens exists is a world in which Mark Twain is identical with Samuel Clemens, because those two expressions, Mark Twain and Samuel Clemens, are both rigid designators. Everybody got that? Okay, now here's the point of all this. If you say pain is identical with C fiber firings, then that statement, if true, must be necessarily true, because pain is a rigid designator and C fiber firings is a rigid designator. It always refers to the same thing. So if the statement is true, then it must be necessarily true. But it isn't necessarily true, even if it were true. It's not necessarily true, because it's easy to imagine a situation in which an animal had pains but didn't have C fibers, and a situation in which an animal had C fiber firings but didn't have pain. So the argument goes, if pain is identical with C fiber firings is true, it's necessarily true. But it's not necessarily true. It can't be. Therefore, pain is not identical with C fiber firings. And if that argument works for pain, it will work for any identity statement at all of the type that the reductionists, that the identity theorists maintain, because they always picked out rigid designators. Pain equals C fiber firings, for example, as the type of identity statement where they thought they could show that mental states were identical with states of the brain. And Kripke is arguing for, in effect, a kind of dualism. He's saying, no, if those statements are true, they'd have to be necessarily true, but they're not necessarily true, so they can't be true. Now, why not? Well, the basic intuition that underlies this is the common sense intuition. Look, feeling a pain is one thing. Having your C fibers fire is something else. Even if they're always exactly correlated, they're not identical things, because the C fiber firing is a different kind of phenomenon from the feeling of pain. So even if they were always perfectly matched, they couldn't be identical, because if they're identical, they'd have to be necessarily identical, but they're not necessarily identical, because you can easily imagine one without the other. Now, that argument has been influential, and the materialists think they can answer it. They think it works against type identity theories, but they think it doesn't work against token identity theories. Okay, now let's take questions about that. I want everybody to understand that. So we've got quite a nice list of arguments against materialism. And again, these are just abbreviations, so you know what I'm talking about. Here's Kripke and the rigid designators argument. And then we're going to get to my favorite, Searle in the Chinese room. But we'll get to that in a minute. Yes?
Is Kripke arguing that pain and C fiber firings are both non-rigid designators?
No. Let me state the point precisely. The expression pain is a rigid designator. It refers to the same thing in all possible worlds. Whereas the thing I get in my stomach when I eat too much pizza, that's not a rigid designator, because I might get a tickle in my stomach. It happens to be a pain in the stomach, but it's not a rigid designator. But the expression pain, that's a rigid designator. The expression C fiber firings, that's a rigid designator, always refers to the same thing. Now, says Kripke, if somebody tells you pains are identical with C fiber firings, well, if that's true, it would have to be necessarily true, because they'd be the same thing. They'd have to be one and the same thing, and not just identifying things by two different properties, like the thing that causes a pain in my stomach. It will just identify... the thing I get in my stomach when I eat too much pizza identifies something that happens to be pain, but it could identify something else. You see that? Okay. Now, here is the argument. If pain is a rigid designator, and C fiber firings is a rigid designator, then the statement, pain is identical with C fiber firings, would have to be necessarily true. It would have to be true in all possible worlds, in all possible situations. But it's very easy to imagine a situation in which it's not true. Indeed, it's probably the case that there are animals that have pains without C fiber firings, and it's certainly not logically impossible that we could make a machine that felt a pain but didn't have any neurons, didn't have any C fibers. Incidentally, I'm always embarrassed to give you this bad neurobiology. I mean, philosophers ought to read the damn neurobiology textbooks. It's just bad brain science. to identify the pain with a C fiber, but let's pretend. Nobody's listening anyway, so we can go through this fantasy example. If I was really going to tell you the story about pains, maybe I will someday. When I first got interested in this, I thought, well, hell, why struggle with all these complicated things like appreciating Proust or feeling the angst of post-industrial men under late capitalism, whatever your favorite sensation is? Why not just take pains and find out how they work in the brain? Well, it turns out, you might have guessed, they're terribly complicated. There's not just one kind of pain. There are lots of different kinds of pains. And there's the A delta fiber pain and the C fiber pain. I don't want to think about pain this morning. It'll give me a pain if I think about pain, but we'll come to that later. So forgetting that this is bad neurobiology, let's imagine somebody saying pain is identical with C fiber firing. They did say that. So Kripke is saying, I think, so far Kripke's winning this argument. Later on we'll see some problems. But the argument goes, if pain is identical with C fiber firing, that statement would have to be a necessary statement, true in all possible worlds. But it's not a necessary statement, because you can imagine a possible world in which somebody has a pain but no C fibers, and somebody has C fibers but no pain. It's simple. It sounds like a big deal, but it's really a simple argument. And in fact, it's a lot like the other guys, because all of them are saying, look, when you give me this materialist story, there's something left over. There's the feeling or the qualia, or what it feels like to be a bat, or what Mary knew when she came out of the black and white room and saw red for the first time. All of these have the same structure. The structure is the materialist account doesn't give you sufficient conditions for the mental phenomena, because you could have a situation in which the materialist account obtained, in which people behaved in the right way, or they had the right neuronal structures, but all the same they didn't have the pain, or they didn't see red, or they didn't have the feeling of what it's like to be a bat. All of these have the same structure. Now the Chinese room's a little bit different, but I'll tell you how it's similar and how it's different from these others. Okay, that's a good question. Other question, I want everybody to understand this. It sounds like a big deal, and it sounds hard, but it's not hard. The idea, I think, is simple enough. Okay, now we're going to zap onto the Chinese room. Here goes. Yeah, sorry.
Given there are different types of pain, can you just argue that pain in an animal is different and so it doesn't require a C-fiber firing?
Yes, I think that is a correct thing to say. But Kripke's argument is supposed to go as follows. Whatever identity statement you make, whatever a statement you make of the form, pain is identical with, and then you cite some material phenomenon, some pain state of the brain, all the same, that couldn't be true, because if it were true, it would have to be necessarily true. Any piece of the brain that you identify with a pain is only contingently identified, because the piece of the brain is one thing and the sensation is another thing. So but says Kripke, if it's not necessarily true, then it can't be true at all, because any identity statement using rigid designators on each side, where you have a statement of the form A equals B, and A is rigid and B is rigid, then if that's true, it has to be necessarily true. And people who do this kind of stuff for a living use a little box for necessary. It's necessarily true that A equals B if A is rigid and B is rigid. Now you see, when they're not rigid, if either one isn't rigid, then in general it's not going to be necessary. Why? Well, if I say Benjamin Franklin is the inventor of bifocals, he was the inventor of bifocals, then that's not necessarily true, because you can imagine a situation in which Ben didn't invent bifocals. Somebody else invented bifocals, and they never got invented. So it'll be necessarily true that Samuel Clemens is identical with Mark Twain, because those were two different proper names of the same guy. But it's not necessarily true that Benjamin Franklin was identical with the inventor of bifocals. That's how things turned out. It just happened that way. Okay, any other questions? Okay, here goes with the Chinese room. Now, did you have your hand up? Sorry, yeah. Why what? Why the expression is necessarily rigid? Yeah. The definition of a rigid designator is something which is an expression that always refers to the same thing in all possible worlds. Now, if you mean the same thing by pain, then it is always going to refer to the same thing, because that's what pain is. It's that which is referred to. Whereas if you take an expression like, the sensation I get in my stomach when I eat a large pizza, suppose that's a pain, then that won't be rigid, because you can imagine a situation in which I ate a large pizza but didn't get a pain in my stomach. So different kinds of things could be the sensation I get in my stomach when I eat a large pizza. But different kinds of things can't be pain, because the expression pain always refers to the same thing. It's not an ambiguous expression. Now, the sensation I get in my stomach isn't ambiguous. It's different entities can satisfy that description. Say some more, and then we'll take you. But first, him. Yes. No, it doesn't matter if. Maybe we got a kind of spectrum inversion here. Maybe your experience of pain is a bit different from mine. For these purposes, that doesn't really matter. What we're supposing is that the word pain has a clear enough meaning so that people can use it to refer to the same thing. And if you like, just take my pains. That'll be a rigid designator, because the expression my pain or pain that I have will always refer to the same thing, namely pains that I have. So the fact that there'll be differences between people doesn't really bear on the argument. Yes, you had your hand up.
It was kind of along with that. I feel like when you stub your toe, that's different pain than if you had a headache.
Yes.
I don't think it necessarily is the same.
Yeah. No. The point is not that all pains feel the same. They don't, but they all have one thing in common. They're all painful. And that's all we need for this argument. And that means there will be something that the word pain refers to, even though it comes in a lot of different varieties. There can be moderate pains and bad pains, pains in your headaches. And I don't want to go through a list of pains. I'll let you think of your own list of pains. But so far, it seems to me Kripke's ahead of the ball game here. Now, these guys I haven't told you the answers to these arguments. The answer they come back with is that his argument will work for type identity theory, but not token identity theory. And that the token identities will be necessary. I'm going to come to that, okay? I'm not going to try to say everything at once. At this stage of the argument, we're going through objections to materialism. And Kripke's rigid designator argument is a famous objection. Okay, now we're going to go to the Chinese room. Now you remember that computer functionalism, or what I baptized strong AI, is the view that really all there is to having a mind is having the right computer program. And what is the right computer program? Well, it is the computer program that will pass the Turing test. Now, some people would say, well, not every program that passes the Turing test, but it has to be the one that is actually implemented in human brains, and we can usually find out what that one is. If we do a computer simulation, we get the psychologists to do reaction time experiments and see that, yes, this is the same one in the computer that is in the human brain. But the basic idea behind strong AI is the brain is a computer. It's a digital computer, and consequently, what we call a mind is just a set of programs. And I put this equation several times on the blackboard. The mind is to the brain as the program is to the hardware. Okay. Now, I like this theory for a lot of reasons. One is you can state it fairly clearly. I mean, a lot of these views that I've been talking about are kind of hard to state, but this one is pretty damn clear. Yes, in my brain right now, they're running a lot of computer programs, or maybe one great big computer program, and that is the mind. So if you can get any other system to implement that program, they'd have a mind exactly like mine. That's how the story goes. And a lot of people still believe that. So that's one thing I like about it. You can state it clearly. And the other thing I like is you can refute it in a couple of minutes. Give me 5 because I'm feeling more relaxed today. But it's one of those beautiful things in philosophy where you can give a decisive refutation in a matter of a few minutes. Here's the refutation. If it were right that all there is to having a mind is having a computer program, then anybody could acquire any cognitive capacity they don't have just by running the program for that cognitive capacity. Everybody got that? That's the idea. I mean, that's all there is anyway. To the mind is a program. So you could have a capacity, you could acquire a capacity just by implementing the program for that capacity. Okay, take me, for example. I don't speak Chinese. I don't speak a word of Chinese. I can't tell Chinese writing from Japanese writing. Now, on the view of strong AI, I could have competence in Chinese just by implementing the right computer program. So let us imagine that I carry out the steps in the program. We imagine that I'm locked in a room, and that in the room there are boxes full of Chinese symbols. Imagine also I have a rule book written in English. The rule book says things like, when you get a symbol that's shaped like this, squiggle, squiggle, put it next to a symbol that's shaped like that, squoggle, squoggle. These are called computational rules over purely formally defined elements. So everybody's got the rules. I'm there in a Chinese room. I got all these boxes full of symbols and a rule book. The rule book, just to look ahead, is called a program. And the program tells me what to do when I get a symbol. Now, outside the room, there are guys who pass in short bunches of symbols, and I look up in the rule book what I'm supposed to do. I got this bunch of symbols, put this one next to that one, that next to that one, and then the rule book says, give them back these symbols. So they pass in symbols, I do a lot of symbol shuffling, and then I give back symbols. Everybody's got the picture. Okay. Now, unknown to me, the rule book is called a computer program. The boxes full of Chinese symbols are called the database. The symbols that the guys hand in from the outside are called questions. The symbols that I hand back are called answers to the questions, and I am called the computer. Now let's suppose that these guys get so good at writing the programs, and I get so good at shuffling the symbols, that after a while my answers are indistinguishable from those of a native Chinese speaker. I pass the Turing test for understanding Chinese. But all the same, I don't understand a word of Chinese. All I do is shuffle symbols. Now, and this is the punchline, this is the point of it. If I don't understand Chinese on the basis of carrying out the steps in a computer program for understanding Chinese, then neither does any other digital computer solely on that basis, because no digital computer has anything that I don't have. What I've got is a program, symbols, a database, a set of rules for shuffling the symbols, for manipulating the symbols, and rules for producing an output on the basis of an input. I get an input, I go through the steps of the program, I give an output, I satisfy the Turing test for understanding Chinese, but I don't understand anything. Okay, that's the refutation. Now let me illustrate. I don't know how long it took me, but it shouldn't be more than 5 minutes. All right, now let's expand on this a little bit. We got to suppose I'm motivated. I'm going to be bored to death in the Chinese room. So I know they give me free beer, or I get paid by the hour or something. But just to keep me awake, they also give me questions in English. And I produce answers in English that are indistinguishable from those of a native English speaker. So they ask me in English, what's the longest river in the United States? And I say, well, It's the Mississippi, but if you count the Missouri as part of the Mississippi, it's the Mississippi-Missouri complex. And they asked me, what's the longest river in China? I don't know I'm being asked that. I just got a bunch of Chinese symbols. And I give them back Chinese symbols that say, well, it's either the Yellow River or the Yangtze River. It's one of those damn two. It's a kind of answer that I guess half-educated native Chinese would give. But I don't know that. I'm just giving back Chinese, meaningless Chinese symbols. Now, what's the difference? In the case of English, I satisfy the Turing test. In the case of Chinese, I satisfy the Turing test. I give answers that are indistinguishable from a competent native speaker. But from inside, there's a huge difference. And why not give the common sense answer? In the case of English, I know what the words mean. I have not just the syntax, but I have the semantics. I have not just the formal symbols, but I have the content. In the case of Chinese, all I've got is the syntax. All I've got is the formal symbols. In the case of Chinese, I am just a computer. Okay, so that's the refutation. Now let me discuss some of the answers to it, because they will reveal the structure of the argument more clearly. Incidentally, I thought of this when I told you I had to go and give some lectures at Yale about artificial intelligence, and I didn't know from artificial intelligence. So I bought a book written by the guys at Yale. And the book showed how they had designed a program. They had designed a program that could answer questions about stories, even though the answer was not explicit in the story. The stories are kind of Mickey Mouse stories, but let me give you an example. A guy goes into a restaurant and he orders a hamburger. When they bring the hamburger, it was burned to a crisp. He stormed out of the restaurant without paying the bill or leaving a tip for the waitress. Now then, that's the story. Okay, now you ask the computer, did the guy eat the hamburger? See, I didn't say that. I didn't say about whether the guy. I just said the guy stormed out of the restaurant, the hamburger was burned to a crisp, and lo and behold, they got a great program. The program says, no, the guy did not eat the hamburger. Now, how does it work? Well, they have what they call a restaurant script. They have all this other information encoded, and the guy the computer matches the question, not just against the story, but against the story plus the restaurant script. Okay, now they argue, so that proves the computer understands the story. It gives answers to the question even though the answer wasn't given in the story. Okay, so I thought, all right, I'll do that. I'll be the computer, and the stories and the script will all be in Chinese. I still don't understand anything. Does everybody see this? In Chinese, I'm just a computer. All I have is a computer program. Anyway, I got to Yale, and I thought, well, what the hell am I going to do to talk for a whole week? This is all I got. And they've surely thought of that. Well, okay. I presented it to them at the Yale Artificial Intelligence Group. There was general consternation. Everybody agreed I was wrong. But they didn't seem to agree on why I was wrong. Everybody had a different argument why I was wrong. Now, let me tell you some of these arguments. I love these arguments. Here is one of the early ones. Actually, I didn't hear this one until I got back to Berkeley, but it's one of my favorites. The answer goes, look, yes, you're there in the Chinese room, and you claim you don't understand anything. But suppose we ask you the question, do you understand Chinese? And suppose you give the answer in Chinese, yes, I understand Chinese. Well, wouldn't that show you understood Chinese? Well, let's try it out. You see, I get Chinese symbols, and I don't know what they mean. But here's what they look like. I get a symbol that looks like this. This will be in a dialect of Chinese that some of you won't recognize. But this unknown to me means, do you understand Chinese? I look up what I'm supposed to do in the rule book, and I give back this symbol. This is in the same dialect of Chinese, so if you don't recognize it, don't worry. It's just a different dialect. This symbol means, do you understand Chinese? This means, of course I understand Chinese. Why do you dumb guys ask me such dumb questions? You know, Chinese, wonderful. You get a lot of semantics in a single symbol. Okay, Now, does that show I understand Chinese? It doesn't seem to me to show anything at all. Okay, but the other answers weren't much better than this. Let me give you. The favorite answer was this. You say you were there in a room, and you had boxes full of symbols, and you had a rule book, and you probably had a whole lot of other stuff. There was a room with windows, table, chairs. You probably had scratch paper for making notes. Now, of course, you don't understand anything. It's the whole system that understands Chinese. You're just like a single atom in the brain of a Chinese speaker. In fact, there's a technical name for what you are. You're just the central processing unit. No one ever thought the CPU could understand anything. It's the whole system that understands Chinese. When I first heard this, I was flabbergasted, and I said to the guy, I was in a public debate, I said, "You mean the room understands Chinese?" "Well, you got to admire courage." He said, "Yes, the room understands Chinese. You don't know any smart rooms," he said. Well, you got to admire courage. I would never have the nerve to say that in public, but it's not going to work if you think about it. Why not? Well, what I immediately said was, okay, get rid of the room. Imagine I work outdoors, I memorize the rule book, I do all the calculations in my head, and I'm in the middle of an open field. There is no room there. There's just me getting questions and giving back answers. It seems to me, in that case, it's exactly the same as the original case. Nothing is added by saying it's the room that understands. And indeed, if you ask yourself, well, why don't I understand? If I'm there in the Chinese room, how come? What is it that I'm lacking? And the reason I don't understand is very simple. In the case of me in the Chinese room, I have no way to get from the syntax to the semantics. I have no way to get from the symbols to what the symbols mean. But, and this is the point, if I have no way to get from the syntax to the semantics, if I have no way to get from the symbols to their meaning, then neither does the room. The room has no way to figure out what any of these things mean. The room has no way. I'll take questions in a minute. I want to go through this stuff first, and then we'll take questions. The room has no way to figure out what any of these symbols mean any more than I do. So that answer was so common, I gave it a name. I called it the systems reply, and that's the one that became the most common in the artificial intelligence community. I thought they would go for the robot reply because it is more behavioristic. And here's how the robot reply went. You were just there in the room all by yourself with all these papers and stuff like that. But forget about that. Suppose we built a robot. A big robot could clonk around and answer questions in Chinese and actually deal with the environment, actually cope with the environment in a way that a human being can cope with the environment. Now, in the case of the robot, you couldn't say it didn't understand, because in the case of the robot, there are causal relations between the environment and the symbol processing, and those causal relations will be sufficient to give you what you say is missing in the Chinese room, namely semantics. Now, I thought that was the argument they would go with, because that's kind of behaviorism, as a type of behaviorism in the robot reply. But in fact, they went for the systems reply. However, the answer to the robot reply is pretty easy, and the answer is, imagine it's a great big robot. And in this robot, there's a great big metal skull. And in that skull is what's called a brain. Only in the brain, in fact, there's a room. And inside the room, there's a guy, me. And I am taking in Chinese symbols, shuffling the Chinese symbols, giving back Chinese symbols, which then go to the output. It's the same situation all over again. I have no way to get from the syntax to the semantics. See, here's the picture. I'm in the robot, and the symbols come in from the robot's visual system. These are converted into Chinese symbols. By the way, I had to learn a whole lot of dumb jargon. People would always snow me with the jargon. Transducers, that's one of the magic words. You've neglected the transducers, they would say. Okay, let's go with the transducers. They have transducers that convert optical stimuli into Chinese symbols. Fine, I'm there with it. Of all the causal relations you like, the Chinese symbols are caused by the optical stimuli plus the operation of the transducers. And then I shuffle more Chinese symbols, give back Chinese symbols to the output system, and the transducers produce physical movements. The robot clonks around, you see, according to the instructions that I give it. It's the same situation. I have no way to get from the syntax to the semantics. And they say, yeah, but we gave it causation. The causation is only relevant if there is a mind that can perceive the causal relation between the input stimuli and the symbols. You see, suppose that my use of the in the story, they're going to ask me questions like, did the guy eat the chicken chow mein? Okay. Now, let's suppose that the symbol for chicken chow mein is actually caused by chicken chow mein. I don't suppose any respectable Chinese would ever eat chicken chow mein. That's an American abomination. But anyway, let's pretend. Okay. Now, suppose it is caused by chicken chow mein. It doesn't make any difference unless there's a mind that can perceive the causal relation. You still have no way to get from the syntax to the semantics. Now, there was another reply that I liked, which I called wait till next year. And that was, well, you're just talking about a particular state of computer technology. But we know from Moore's law that computer technology improves, it doubles every 18 months. The computer power will double in 18 months. And so come back in 18 months and we'll have a better computer that will answer the Chinese room. That's no good either, because my argument has nothing to do with any particular state of technology. It has to do with a definition of computation. Computation, you remember, is defined as formal symbol manipulation. Usually thought of as manipulating zeros and ones, but it could be anything. It could be Chinese symbols or anything else. Any type of formal symbol manipulation can be computation. The argument has nothing to do with a particular state of technology. You can change the definition of computation, but under the existing definition of computation, under Alan Turing's definition of computation, then in the Chinese room I can have all the computer power you like, and I still don't understand anything. Now, the arguments in philosophy ought to have a structure, and this one does, and I'm going to tell you the structure of the argument. Here it is. The argument says, programs are purely formal or syntactical. And I'll just write that as syntactical. But minds have semantics. That is, they don't just have, let's just say, minds have meanings, and we'll call that semantics. But now, both of these, I think, are true by definition. I mean, the program is defined as a set of rules for manipulating symbols, and minds, as we normally understand them, contain semantic contents. They don't just have meaningless symbols. But now, what the actual argument shows is that the syntax by itself, the syntax, just shuffling the symbols, is not the same as, nor is it sufficient for semantics. Syntax is not sufficient for, nor identical with semantics. But guess what? It follows from that programs by themselves, programs are not sufficient for, nor the same as, minds. So programs are purely formal or syntactical. Minds have meanings or semantics. Syntax is not sufficient for semantics. I'll take questions in a second. I want to get it all out. And that was what the argument is supposed to show. The argument is supposed to show the guy has all the syntax you can give him. He's got all the symbols you want to give him. He shuffles away cheerfully because he's paid and he gets free beer or whatever. But all the same, he has no way to get from the symbols to the meaning, from the syntax to the semantics. But if the syntax is not sufficient for the semantics and not constitutive of the semantics, then it follows that the programs are not the same as minds, nor are they sufficient for minds. It's ludicrously simple, this argument. And I think, I thought, that either they got to just ignore it, or they got to change their minds. It took 30 years, but they're starting to come around now. As I told you, I recently got an invitation to address an international conference on artificial intelligence, and they say, well, most of the people in AI now agree with you. Well, that's nice. It took them a long time, but anyway, I don't know enough about contemporary research to have an intelligent opinion, but this is a purely philosophical argument. Okay, let's take questions. I saw a lot of hands up. You were first, and then there was somebody. No, there was a guy back there. Let's start with you, because you had your hand up now.
It seems to me that the argument definitely holds for a more simple system, but what if the books had like pictures?
Yeah.
Something that you could understand first, and that's how you get it.
Yeah. Who interprets the pictures? See, this is the problem. If the picture is defined as just a set of marks, then you need an interpreter. But if the picture is supposed to be, as it were, intrinsically semantic, then no picture satisfies that condition. See, something is a picture only relative to our interpretation. It exasperates me that my dog Gilbert, intelligent dog that he is, he can't recognize me in photographs. He can't even recognize himself in photographs. So the ability to recognize a picture is itself a remarkable ability. But anyway, go ahead.
I guess I just meant, once you see the picture, it first becomes electrical firings
Yeah.
in your eyes.
Yeah.
In the same way that it would in a sensor.
Yeah.
I don't know.
Okay, no, well, let me go to the next step. In the case, you see, another argument against me goes as follows. Look, what does the brain do? Well, the brain has a series of neuron firings. They either fire or they don't. It's like zeros and ones. But that's all that's going on is a set of neuron firings, and we can simulate that in the computer. But there's this difference. In the case of the brain, the neuron firings end in an actual understanding. They end in an actual semantic content. And that's what you don't get in the computer. There was another answer. I've given you four. The systems, the robot, wait till next year. But another favorite answer was the brain simulator. And the brain simulator says, look, suppose we did a computer simulation of the Chinese brain. We took the brain of a Chinese and did a simulation, as philosophers love to say, down to the last molecule, any degree of accuracy you like. Wouldn't that understand Chinese? And the answer is, what does it simulate? All it simulates is the formal structure. But simulation is not duplication. You have to duplicate the causal powers, and it doesn't do that. You see, we do simulations of flight, simulations of 5-alarm fires in Oakland, simulations of rainstorms, but a computer simulation of a rainstorm won't leave us all wet. And a computer simulation of a fire won't burn the buildings down. It's just a formal simulation. And a computer simulation of a brain stands to an actual brain the way a computer simulation of flight stands to actual flight or any other real phenomenon. One more try, and then we'll go to somebody else. Yeah.
If you could, chemically build the brain.
Yeah.
And if you're saying that's different still because
Okay.
it doesn't have an understanding, isn't that dualism?
All right. Well, we'll wait and decide what the implication of this. Let's just get the argument out. I don't think it leads to dualism, but it certainly leads to a rejection of a certain type of materialism. Suppose you built the brain out of nucleoprotein. You built the computer out of nucleoproteins, just like ours. Then I would say, if you can duplicate the causes, you can duplicate the effects. But the whole point about the computer is that it's purely formal. Hardware implementation is irrelevant. This is not a weakness of computation, it's the strength of computation. It's not a weakness of computation that is purely formal. It's why the damn things are so powerful, because they can do formal symbol manipulation at the rate of literally millions per second. I say that, I still don't know if I believe it, but all the guys who know about this and do it for a living tell me that's true. Yes, millions per second. And I can't do that. But the power of the computer is precisely what makes it weak here. Now, she had a question. Yes?
I'm just kind of wondering, what's the structure of the rule book? What's actually in there? Is
Yeah.
English in there, or
The rule book is written in English, and it gives me a set of rules for manipulating Chinese symbols. So the rules will say, you have a big piece of tape, and when you get a symbol that looks like this, put it next to a symbol that looks like that, and then move to the next place on a tape, and then see what you're supposed to do when you have two symbols like these two, and then do that. This is what computers do. This is why computers are so powerful. They don't have to care what anything means. They just move one square to the left, one square to the right. They erase a 1 and print a 0, or erase a 0 and print a 1. And what I'm imagining is a guy is doing the equivalent of that in Chinese. Now, you see, I'm a very literal person, and when they tell me, well, that's what a Turing machine has, it has a tape and a lot of zeros and ones, my immediate impulse is to take the damn laptop apart and find the tape and the zeros and ones. Well, it's not there. That's not the way it works. The way it works is it has something that is functionally equivalent to zeros and ones, and those will be voltage levels. So 4 millivolts will be a 0, 7 millivolts will be a 1, and the shift from 4 millivolts to 7 millivolts is called a state transitions, and that's what the computer does very rapidly. It goes through millions of state transitions, and it's a wonderful piece of machinery. I mean, we couldn't live without it. Okay, first her, and then you, and then you. Yes?
Okay, so say you are in this Chinese room,
Yeah.
and you are getting these symbols, and you're spitting other symbols out. Isn't it possible that after reading a question so many times you begin to understand what those symbols mean?
Okay, here is another answer I heard, and that is, well, look, if you were there in the room, it's after a while you're kind of going to guess what these guys are driving at. Well, you might, but the name of that is not computation. That is, you might think, why do they keep giving me this same dumb symbol over and over again? And you might come to a hypothesis about why they're doing that. But the way I've described it, you'd have to be some kind of a mind reader or a genius to figure out what they mean. But in any case, even if you do, that's not computation. Computation is formal symbol manipulation. That's not its weakness, that's its power. Now, every so often you're going to read in the newspaper that some new computer program has achieved some incredible feat, and it's always put, this is a threat to human dignity. And my favorite was Deep Blue. The IBM guys invented, they had to build special hardware. It was a big deal to do this. They had to build special hardware and design a program that would play chess. And they finally got a program that could beat any human chess player. Now, I got calls from newspapers all over. Fortunately, I was in Paris at the time. They couldn't track me down. But I did get calls saying, isn't this a blow to human dignity that this last talent that humans have, chess playing, has at last been taken over by the computer? And I said, look, any pocket calculator can defeat any mathematician that ever lived in speed of arithmetical calculations. Is that a blow to human dignity? It's a bit like saying, I can't run as fast as my Porsche. Do I feel, I'm humiliated. It's ridiculous. It's just ridiculous. You see, the thing to remember is this. The pocket calculator doesn't calculate. The calculation is all in our interpretation. All the pocket calculator does is a series of electrical state transitions. And we pay the money to buy these things. They're pretty cheap now because we can use them. We can use the state transitions as calculations. But the pocket calculator doesn't know that it's doing long division. It has no idea. Why doesn't it know it's doing long division? Because it doesn't know anything. All it is a hunk of junk. It's an electronic circuit that goes through electrical state transitions. End of the story. Now, we have made these things so we can interpret them in certain ways, so we can use them for certain purposes. But the machine itself isn't doing any calculating. The calculation is something we do with the machine. Now, similarly, the machine doesn't literally play chess. It doesn't know, oh my God, the guy's castled on his king's side. Should I castle on the queen's side? Or, oh, it's a Rui Lopez opening. Why doesn't it know that? It doesn't know anything. All it has is, I'll tell you how Deep Blue worked. I found out a bit about it. They won't tell you everything, but they'll tell you some things about how Deep Blue works. And the point is, it doesn't know that it's playing chess, and in any literal sense, it isn't. It's just a big piece of machinery that goes through a lot of electrical state transitions, and we've found ways to interpret them. There's going to be a new one that's going to come out in a few weeks, and I've arranged that newspapers can call me up and ask me the deep significance. It's some damn fool thing they've done. I admire the technology of this, but it's got no psychological significance whatever. And the guys who do it are constantly amazed that the goalposts are always being reset. People say things like, well, there's always something the computer can't do. And then there's your favorite thing. It can't fall in love. It can't have a sense of humor. It can't feel the angst of post-industrial computers under late capitalism. But it's very easy to program a computer to all these things. Say, I'm in love, or ha-ha, or I feel the angst, of, whatever. Whatever you want, you can program a computer to do, somebody will do it. But as soon as they do this, as soon as the programmers do this, people say, well, that one didn't really count. Now there's something else that the computer can't do. And the AI guys feel legitimately the goalposts are being moved on us all the time. And that's right. But it's beside the point. The point is not that the computer gets almost to the human level, but it can't quite get over that last step where it's truly in love. No, that's not the problem. The problem is it doesn't get started. It's not in that line of business. It is a formal symbol manipulating device. All that's actually happening is a set of electrical state transitions. End of the story as far as its intrinsic operation is concerned. The rest of it is all in our interpretation. However, this was another answer that was given to me, was the brain simulator. And the answer is, it depends on which features of the brain are being simulated. And if it's just the formal features, the computational features, then of course, it's just like the simulation of anything else. A brain simulation no more thinks than a flight simulation actually flies, or a rainstorm simulation actually rains. Simulation is not duplication. And indeed, for those of you, I think in very simple sentences, and there are 2 4-word sentences that summarize this whole argument. Syntax is not semantics. That's the first thing to remember. And the second is simulation is not duplication. You can simulate as much as you like, but that doesn't actually duplicate it. Now, there are a lot of other hands up, and I don't want to... somebody... yeah, you're next. Yeah.
I understand how this really shows the futility of Turing tests in ascertaining intelligence.
That's right. It is, incidentally, a refutation of behaviorism.
And also, I see that it can... For me, it means that computers don't understand.
Mm-hmm.
But what really is understanding? What are the necessary and sufficient conditions for understanding?
That's the second half of the course. The first half of the course, I tell you what all these other guys worry about. The second half of the course, I want to tell you what really worries me. But we're not there yet. I'll tell you what understanding is later. There's a key word, intentionality. And there's a book on the subject I recommend that you read. It's got that in the title. Okay, now you were next. And then the guy at the back of the room. Yeah.
Does a strong AI theorist have a different definition of computation compared to the weak AI theorist?
No. This is, again, a very good question, and let me repeat it for people in the back. I distinguish between strong and weak AI. Weak AI is the view that you can simulate the mind on a computer, and that this is very useful in studying psychology in a way that the computational simulations are essentially useful in studying anything. Just about any department in this university in the sciences uses computer simulations. You can't do molecular biology nowadays without computers. But that's weak AI. Strong AI says the simulation is the real thing. If you can simulate a mind, you have created a mind. Now, her question was, well, do they have a different conception of computation? No, they have exactly the same. This is the beauty of computation. It is a well-defined notion. And indeed, you can take courses in this university that will teach you how to do it, how to do computer programming in such a way that the program gives the machine a set of instructions as to how it is to compute certain functions. Yes?
But my understanding was that the difference between strong AI and weak AI is that the strong AI actually perceives, has a cognition, and understands what's going on. So you're saying that the strong AI also says programs are just formal.
Yes.
They're only syntactic.
Exactly, and that's the weakness of strong AI. Well, here, let me go through it. You see, if you look at the history of this, when the history of this has been written, the standard objection to strong AI was always there's some area that the computer can't reach. There's always some little corner of the human soul outside the reach of the computer. I never made that objection. My objection was always, look, imagine any success you like. Imagine you get a perfect computer simulation of human cognition so that you pass the Turing test in every known respect. All the same, you have to distinguish between the computer as a system that does formal symbol manipulation and the human mind that actually has semantic contents. Now, the weakness of those guys, the reason they failed, is they said, what I think once you say it out loud is obviously false, formal syntactic manipulation by itself is sufficient for and constitutive of semantic content. And once you see that, it's obviously false, and indeed that's what the Chinese room argument shows. It shows it's obviously false because you got all the symbols you want, you pass the Turing test, but you don't have any semantic content. You don't understand anything. Okay, this is fun, so there are more questions. Here, she has one. Yeah.
Yeah, this is a little bit different.
Yeah.
But I'm just kind of wondering, what about animals and how they do things? Like a parrot can be taught to respond to certain things, but it doesn't understand. How does that kind of brain function relate?
Yes. What about animals and animal computations and so on? And the truth is, we don't really fully understand animals yet. There was a period when people had this Cartesian mistake of saying, well, maybe animals don't really think and don't have mental states. All they got to do is turn on the damn television set, and you see animals doing all kinds of things. Like all experts on the subject, I get it from television, where you see all these things done with these primates, and they are marvelous, and they do obviously have mental states. But what actually is going on in Gilbert's doggy brain? Well, I make the mistake of all dog owners. I anthropomorphize. I think, well, he must be worried about the same things I'm worried about. But of course, he isn't. He's got a different set of worries. We don't really know what goes on in the animal brains. And the scary thing about the damn parrots are, it looks like that the really smart ones, that one, I forget her name, Irene Kloppenberg or something like that. If Jennifer was here, she'd remind me that you get quite remarkable cognitive achievements on the part of the parrots. It's not just mimicry. But the short answer is I don't know. I don't know enough. Look it up. I mean, why don't you do the research on it and report back? Okay. Other questions? Now, a whole lot of hands up. Didn't I promise a guy at the back? Yeah. Speak loud. I can't hear.
Take like a native Chinese speaker. What's to say they're not doing the same thing as what you're doing in the room?
Yes.
Inside their head, but really quickly so that you think they understand.
In the case of native Chinese speakers, they have something I don't have, and that is they know what these symbols mean. They understand them. When I first went to China, I thought I'd lecture about this, and I didn't want anybody's feelings to be hurt. So I decided to call it the Arabic Room. But that was a waste of time because They all knew. They had all read the Chinese. They all knew about it. And this was in 1988, and it was pretty funny because you didn't have, as we do, an audience where everybody can talk. You sat around in these big easy chairs, and they served tea, and then we went around the room, and I'd ask, well, what does everybody want to study? And it was very interesting the different answers you got. One, I say, well, what would you like me to talk about? And the first guy would say, I want you to talk about Kripke's criticism of your account of names using his rigid designator argument. That was the first guy. The second guy said, I want you to talk about the thought of Mao Zedong. He's the secret policeman. Okay. You could tell. You could tell. Who were the professional intellectuals and who were the secret police by the level of their philosophical sophistication. And I was astounded by how much, this was in 1988, before all kinds of things happened. And I was astounded by the level of sophistication of the real intellectuals. The secret police, they're like the secret police anywhere. They just mouth what they're supposed to mouth. I don't know how we got off onto that. But anyway, here we are back in the Chinese room. Anyway, I want you to see all these replies. The systems reply, the robot reply. Wait till next year in the brain simulator. But one of the important things I want to emphasize is this has nothing to do with any state of technology. No matter how fast the computer works, it's still manipulating symbols. And to repeat, that's not a weakness. That's why the damn things are so powerful. It does a long division much faster than I can, not because, boy, it thinks really hard. And it thinks, God, the guy, he asked me another long division question. Why does he keep straining me? Doesn't think anything. It's just a hunk of junk. It's an electronic circuit that we have programmed to do all this stuff. You had another question. Yeah.
Well, I was just curious, if you gave a computer, say, one of its functions is to stay alive, and you gave it an ability to get its own food from the sun,
yeah,
all of a sudden things would start to take a little more meaning for it if it knew that it had to do something.
Yeah.
I guess that's what I'm saying. Maybe it's not really understanding.
Yeah.
We have these values.
You see, I did everybody at the back hear the question. The point is, suppose you had to design a computer that was, so to speak, self-sustaining. It would do the things necessary to repair itself and reprogram itself. We've already got such computers. All the same, it is purely formal symbol manipulation. Now, of course, maybe there's something going on in there I don't know about. That's not the point. The point is, what does it have solely in virtue of being a computer? And what it's got is formal symbol manipulation. Let me go through some misunderstandings. A lot of people think I'm trying to show computers can't think. That's not it. We're all computers, and we can all think. If computation is a computer is defined as anything that does computation, and computation is defined in the usual sorts of ways, then I'll show you a computation. I write down 1 plus 1 equals 2. That's a computation. All the computers in the room raise your hand. We're all computers. Okay. So the point is not that computers can't think. Of course, anybody who thinks can also compute. Therefore, anybody who thinks is a computer. Indeed, I would say only computers could think. If you couldn't compute anything, you couldn't think at all. So the point is not that computers can't think. Can you build a thinking machine? Why not? We are thinking machines. If you could build a machine like us, then you would create a thinking machine. Yes, but could you build a thinking machine out of some different material? We don't know the answer to that. But the question, can you build a thinking machine out of something other than nucleoproteins? We ought to hear like the question, can you build a heart that pumps blood out of something other than muscle tissue? We've already done it. The reason we can do it is we know how the heart works. We don't know how the brain works, so we don't know how to build an artificial brain. But I'm not arguing that computers can't think. On the contrary, only computers can think. I'm not arguing that machines can't think, because we are machines and we can think. And I'm not arguing that you couldn't build an artificial machine that thinks. We don't know. We ought to hear that question. I like the question, can you build an artificial heart that pumps blood? The answer to the second question is yes, we don't know about it. Artificial brains, because we don't know enough about the actual brain. Okay, but now then, what is the argument? The argument shows that computation by itself, computation as standardly defined as the manipulation of formal symbols, is not by itself sufficient for nor constitutive of thinking. And that we know independently. We know that syntax is not semantics. By the way, for those of you who like this kind of stuff, there are formal proofs in mathematical logic that the syntax is not sufficient for the semantics. It's called a Skolem-Lowenheim. The Skolem-Lowenheim theorem is supposed to prove that. But it's an obvious point anyway, and the Chinese room illustrates it. Just having the syntax is not enough to have the semantics. Okay, well, there's still some questions about this, so let's take at the back. This guy, yeah. Yeah.
With the symbols. So it's sort of like you're limited in your semantics, but there's still
some semantics, yeah. The way that I defined it, there's nothing in the rule book that tells you what the symbols mean. You see, the symbols don't tell you, and by the way, this symbol stands for hamburger. It just says this is what you do with that symbol. The rule book is written in English, so that's because the computer in question needs to have the rule book in English so it can implement the program. But the actual rules do nothing to specify the semantic content of any symbols. In that respect, they're like the rules in a computer. Now, there's a deeper point I haven't made, and that is, I want to make it now because we got a few minutes. Computation doesn't name a natural phenomenon. It's not a phenomenon like digestion. Computation is always in the mind of the observer. Computation is not discovered in nature. It is assigned. And the proof of that is that anything at all can be interpreted as a computer. In the old Chinese room days, I used to be invited around the country to debate all these guys on. And it was more fun than anything because I didn't really have any doubts or any problems. But at some point in the debate, I would take a piece of chalk or a pen or a thing like that. I'd slam it down on the table and say, "That is a digital computer." It just has a boring program. The program says, stay there. Okay, one-step program. And of course, anything is a digital computer. What? A digital computer is anything you can assign a computational interpretation to. So we'll call that one 0 or 1. It's a very boring computer program. But now, it's less dumb if you think about it. Anything at all can be construed as computing a function. Watch, here's a computer. This piece of chalk just computed the function. It's a well-known function. It computed the function s equals 1/2 gt squared. The distance that the piece of chalk falls is equal to half of the gravitational content times the square of the time that it falls. Isn't that called Galileo's law? There's a name to that. I learned it in physics. But in any case, this will compute that function. But if this is a computer, then anything is a computer, because anything can be described in a computational way. Computation is not discovered in nature. Computational interpretations are assigned to phenomena, and it's not arbitrary. We design very expensive pieces of machinery so that we can interpret them computationally. This is a separate argument from the Chinese room argument. It's actually a deeper argument, and I haven't had so much attacks on it because most of these guys don't get it. But you will get it, so let me tell you the two different arguments. The Chinese room argument shows that the formal syntactical steps of the computer program are not by themselves sufficient for semantic content or semantic interpretation. This argument shows something much deeper than that. Namely, the computational interpretation is in the mind of the interpreter. The natural phenomena, the state transitions in the electrical system or the piece of chalk falling, they're just natural physical phenomena in the world. We can assign a computational interpretation of them. The Chinese room argument showed the semantics is not intrinsic to the syntax. This argument shows the syntax is not intrinsic to physics. Syntax is not something you discover in nature. It's an interpretation you assign. That doesn't mean anything goes or it's arbitrary. No, on the contrary. Only certain things will carry out certain computations. But computation does not name a natural phenomenon like force, mass, or gravitational attraction. Now that's the deep point, so I'm going to repeat it. It's boring when lecturers repeat things. But the 2 points are: the program and the computer are defined in terms of syntactical symbol manipulations, and the syntactical symbol manipulations are not sufficient for semantics. You have to add the semantics. But this is a deeper point. This says syntax doesn't name a feature of physics. The syntax is in the eye of the beholder. Syntax is not something you discover in nature. It's something you assign to nature. So as I said, I think in simple slogans, and the 2 slogans are that the syntax is not by itself sufficient or constitutive of the semantics, and this argument says the physics by itself is not sufficient for nor constitutive of syntax. The syntax, just as the semantics is not intrinsic to the syntax, so the syntax is not intrinsic to the physics. Okay, next time we'll go on.